All right, welcome back to another lecture. I'm recording from my office today, and sometimes the hall gets a little noisy, so I apologize if you hear some commotion out in the hallway. I'll try to speak over the din as much as possible. But let's get into section 3.2. In this section, we're going to talk about developing a one-sample hypothesis test for the mean. In the previous section, we developed some steps for hypothesis testing in general, and we talked specifically about a one sample hypothesis test for the proportion. But these were the steps that we developed for a one sample hypothesis test. And so these are the same steps that we're going to follow for the mean. And so, this one should go a little bit more quickly than the previous one did. The main thing that we need to develop here is just how to compute the p-value, because otherwise the steps are the same for this test, right? So all we need to really do is discuss how to compute the p-value, and then we can run a few examples. So just like with lecture 3.1, we're going to do a few examples where we're kind of developing some steps, but at the end of the section, I think it's examples 3 and 4, we'll run a hypothesis test from beginning to end. So if you're trying to complete a homework assignment and you want to follow along with an example, those would be the examples to look at, right? Just flip all the way to those ones. Make sure that you have your notes ready to go, and also there should be an Excel file with some data in it for this particular section, because one of the examples that we'll do will have data. So make sure you have that downloaded and ready to go as well. And without further ado, let's get into it. So just to give us a little motivation, right? Let's take a look at a couple examples. Number one here says an agricultural company, or chemical company, believes that they have developed a fertilizer that causes corn stalks to grow taller. They test this fertilizer on 15 corn stalks of a certain variety whose mean height is 2.7 meters with a standard deviation of 0.5 meters. The fertilized corn stalks have a sample mean of 3.1 meters. Is this enough of a difference to say the fertilizer is effective? Okay, so again, you can pause the video and make sure that you're absorbing all that information. But the idea is usually these corn stalks grow to be 2.7 meters, but we apply a particular fertilizer to them that causes them to grow to be 3.1 meters. And so the question is that enough of a difference for us to say that the fertilizer works? Okay. Let's look at another scenario. It says, on average, it takes a person 58 seconds to solve a particular kind of optical illusion, autostereograms, right? I don't know if you've ever seen the Magic Eye books, but you can kind of Google that and get a picture. They were really popular when I was a kid. Anyway, an elementary school teacher thinks that because students have good imaginations, they'll be able to solve these illusions faster. To substantiate her hypothesis, she records the time it takes 30 students to solve an autostereogram. The mean was 55 seconds, and the standard deviation was 5 seconds. Is this good enough to say that her students are able to solve optical illusions faster than average? Okay, so again, the population mean amount of time to solve one of these puzzles is 58 seconds. Her students were able to solve it in 55 seconds on average. Is that enough of a difference to say that her students are really, truly better at solving these kinds of puzzles? Or is it just, that she just so happened to get 30 students who were really good at solving these puzzles? So we'll run hypothesis tests, of course, to answer those questions. And the key to being able to answer them is to compute the p-value. So this is the same definition that we went over in 3.1. I'm giving it to you twice, and that should tell you how important I think it is, right? So the p-value of a hypothesis test is the probability of collecting a random sample that yields the sample statistic that we obtained, or something more extreme than that, assuming that the null hypothesis is true. In this case, since we're testing means, the sample statistic in question will be the sample mean. Okay, so the p-value, we calculate the p-value by, first of all, assuming that the null hypothesis is true, and then operating under that assumption, we calculate the probability of getting the sample mean that we got. And if we end up with a really small probability, then that tells us, well, it was probably wrong to assume that the null hypothesis was true. And so we reject the null hypothesis. Once again, I've given a chart here to try to describe in math symbols how to compute the p-values. And once again, these are probabilities that we've seen before. These are the kinds of probabilities we've seen before. So I'm using a heart here to represent the sample mean and a star to represent what we're assuming the population mean to be. But anyway, we've calculated these kinds of probabilities before. The two-tailed test is, once again, kind of a complicated scenario here. But, I'll show you a shortcut in Art of Stat in a second on how to compute these, so you won't have to do a lot of these by hand anyway. But let's take a look at, actually, before we take a look at some examples, I did want to hone in on this p-value situation a little bit more. And I'm going to try to do this as we go through the material in this unit. As we become more and more familiar with hypothesis tests, we can talk a little bit in a little bit more and more detail about the logic behind what's going on. So when we compute the p-value, the only mathematical assumption that we make is that the null hypothesis is true. I'm mentioning this because you might have this thought. I've had students in the past who have had this question. The question they ask is, well, if we get a small p-value, then that indicates something strange is going on. So why would we reject the null hypothesis? Why wouldn't we just say that, well, there must be something wrong with our sample? And the answer to that question is, that's a good point, right? Like, it could just be that there's something wrong with our sample. But as the statistician in this process, that's not really our job to evaluate. What we're evaluating is if we assume, right? So given that the data is what it is, right? If we assume that the null hypothesis is true, what's the likelihood that we would have obtained that data? I think in the real world, it's good to scrutinize studies, and it's good to scrutinize the way that data were obtained. But from a mathematical standpoint, the only mathematical assumption that we're making is that the null hypothesis is true. So if we get a small p-value, we should reject the null hypothesis, okay? Since that's the only thing that we assumed. The data aren't assumed, right? They were observed. Okay, the null hypothesis is the only thing, mathematically speaking, that we're assuming. Okay, so with that in mind, now let's look at a couple examples, and we'll practice computing some p-values using the techniques that we learned back in Chapter 2. And then I'll show you a shortcut way to do it in Art of Stat. Okay, so part A. It's the same scenario that we started the discussion with, right? An agricultural company puts some fertilizer on some corn stalks to see if they grow taller. And so we want to compute the p-value for this scenario. Let's also state the hypotheses, the null and alternative hypotheses, okay? So this would be step 1 of our hypothesis testing procedure, right? We would say, well, the null hypothesis. Now, we're not going to say p equals something because we're not testing p. We're not testing proportions, right? We're testing means. We're testing mu, right? So we're going to say mu equals whatever the original claimed value was, which I believe was 2.7 in this case, right? Corn stalks usually grow to be 2.7 meters tall, supposedly, right? So we'll say, yeah, when you put the fertilizer on, there's going to be no change, no difference. The corn stalks are still going to be 2.7 meters tall. The alternative hypothesis is going to be that the fertilizer works. In other words, it causes the corn stalks to grow taller, right? Mu greater than 2.7. And now the next, I guess, obvious question to ask is, well, what's the sample evidence that we have in favor of the alternative hypothesis? And the sample evidence is that, well, in our sample mean of corn stalks, or in our sample of corn stalks, the sample mean was 3.1, right? And that is certainly bigger than 2.7, right? So is this good enough evidence? Well, we would have to compute the p-value. So the p-value is going to be the probability that we obtain that sample mean, 3.1, or something more extreme than that, right? So if 3.1, notice that 3.1 is bigger than 2.7. So if 3.1 is extreme, then anything larger than that would also be extreme, okay? So we want to compute the probability that x bar is bigger than or equal to 3.1, assuming that the population mean is 2.7. And once again, we've seen these kinds of probabilities before. We usually didn't write down the conditional part of the probability. Usually we just wrote them down this way, right? But we know how to compute these. We know that X bar is normally distributed, so we can use the normal calculator to compute this probability, provided that we know what the population standard deviation was. And in this case, I think we do know that, right? Because we're told they test this fertilizer on 15 corn stalks of a certain variety whose mean is 2.7 and whose standard deviation is 0.5. So in this case, we are given the population standard deviation, right? We know what sigma is. So we can go ahead and use the normal distribution. Okay, so I'm going to go to Desmos, and I'm going to use the normal dist, okay, with a mean of 2.7 and a standard deviation of 0.5 divided by square root of our sample size. Our sample size was 15. Okay. So, and then we're going to compute the probability that X bar is greater than or equal to 3.1. So let's see what we get in Desmos. So I'm going to use the normal dist with a mean of 2.7 and a standard deviation of 0.5 over square root of 15. Okay, I can zoom in on that, and then we'll look for the probability of obtaining something greater than or equal to 3.1. And there we go. There's our p-value. If we want 4 decimal places, we can click on the little down arrow. But yeah, that would just be 0.001. 0.0010, right? If we round to 4 decimal places. Okay, and that's that. We weren't asked to make a decision or write a conclusion or anything. We were just asked for the p-value. So that's how we would do it. Okay, let's look at another one. Part B is the more it's the more kind of standard kind of setup, because usually we won't know what the population standard deviation is. Let's see. It says on average it takes 58 seconds to solve a particular kind of optical illusion. A school teacher thinks that because children have good imaginations, they can solve them faster. So she records the time it takes 30 students to solve an autostereogram, and the mean was 55 seconds with the the standard deviation was 5 seconds. So notice that we are given a standard deviation here, but it's not the population standard deviation. This is the sample standard deviation of her 30 students, right? So this standard deviation is the sample standard deviation, S equals 5. Okay. Well, I'm getting ahead of myself a little bit. Let's write down the null and alternative hypotheses, right? The null hypothesis is that, no, her students aren't going to solve this any faster than normal other people, right? Their average time is going to be 58 seconds. The alternative hypothesis is that, no, they are faster, right? Their mean time to solve the puzzle is going to be quicker, right? Less than 58 seconds. And the sample evidence we have in favor of that alternative hypothesis is that it only took them 55 seconds, right, when she collected a sample of 30 of her students. So let's see if that's good enough evidence, right? The p-value is going to be the probability of obtaining that sample mean or something more extreme. Now, in this case, 55 is less than 58. So if 55 is extreme, then anything smaller than 55 would also be extreme, right? So this is the probability that we want to get, assuming that, right, given that mu equals 58. Now, the problem here is that we don't know what the population standard deviation is. We only know what the sample standard deviation is. And so we don't use the normal distribution for this. We're going to use the t-distribution for this, right? We'll use the t-dist with a mean of 58 and a standard deviation of S divided by square root of n, right? N was 30 in this case. And I think we also have to put in the degrees of freedom. In fact, the degrees of freedom might come first. I can't remember. I can't remember, you guys. Maybe we have to put the degrees of freedom first. Our sample size was 30, so we have 29 degrees of freedom. And then we put the mean and then the standard deviation. Okay. I could be wrong, but either way, we'll go over to Desmos and we'll fix it if we need to. And then we're going to look for the probability that X bar is less than or equal to 55. Let's take a look. So I'm going to use the t-dist. And yes, we have to put degrees of freedom first, right? 29 degrees of freedom. 58 was the mean. And the standard deviation was 5 divided by the square root of 30. Okay, so there's our t-distribution. And we can compute the probability now that X bar is less than or equal to 55. So that's interesting, right? So once again, we're getting 0.001. If we wanted to go to 4 decimal places this time, we could call it 0.0013, okay? So let's write that down. Okay, so there's our p-value. Okay, so as I said a moment ago, scenarios like this one that we just did, where sigma is unknown, are much more common than scenarios like 1A. And so consequently, we're just going to use students' t-distribution as our default when we run these kinds of hypothesis tests. When we go to run these in Art of Stat, we'll use the inference for a mean app. And the default setting of that app is to use students' t-distribution to calculate the p-values. Okay, and this is why we call these t-tests, right? So we call a test for a mean a one-sample t-test. It's because we're using students' t-distribution to calculate the probabilities. Or rather, Art of Stat will be using students' t-distribution to do that. Let's just go over to Art of Stat and rework problem part B here to make sure that we get the same value when we use Art of Stat to do it. So I'm going to go to artofstat.com. I'm going to go to web apps, and the inference for a mean is right next to the inference for a proportion. So you have to scroll down a little ways till you get to these confidence interval and significance tests for one sample. And this time, instead of doing inference for a proportion, we want to do inference for a mean. Okay, so we'll click on that one. And we don't want an example from the textbook. We have our own summary statistics. Let's see. The sample size was 30. The sample mean was 55. And the sample standard deviation was 5. Okay. Now, we don't want to run a confidence interval. We want to do a hypothesis test, which is called a significance test in the app. The null value, well, in our null hypothesis, we said mu equals 58, so the null value is 58. And we wanted to see if the students could do it faster, right? So we wanted to see if mu was actually less than 58. So you make all those changes. You can make sure that the alternative hypothesis is stated correctly here, and it looks like it is. And then you can see the p-value, right? 0.0013. It's also given down here. And sure enough, right, that matches exactly what we got when we did it ourselves, right, through Desmos. But it's a little bit easier, I think, to do it through Art of Stat and get the p-value that way. So that's how I would like for you to do it in the future, okay? Okay. So moving on, let's just do a couple examples. First of all, here are the steps for running a one-sample hypothesis test on a mean, right? Same steps as for a one sample hypothesis test for a proportion, right? You're gonna first of all determine the null and alternative hypotheses. The second of all, gather the sample evidence. In this case, the sample evidence is going to be a sample mean rather than a sample proportion because we're testing means. And then step 3 is to compute the p-value. We'll use the inference for a mean app from Art of Stat to do that. But behind the scenes, what that app is doing is it's computing the p-values like we did a second ago, right? We'll just let it do the heavy lifting. Then step 4, we'll make a decision. We make our decision and write our conclusion in steps 4 and 5 the same way that we did for the previous section. If our p-value is less than alpha, we reject the null hypothesis, which means there is sufficient evidence to support the alternative. If the p-value is not less than alpha, then we do not reject the null hypothesis. So there's not sufficient evidence to support the alternative. So let's look at a couple examples where we run those from beginning to end. So number 2 here says, a student read that in 2020, the average cost of a 2-bedroom apartment in Visalia was $1,275 per month. She suspects that price has gone up. To test her hypothesis, she randomly selected 16 apartment complexes and found that they charge an average of $1,300 per month with a standard deviation of $23 per month. Okay, so it looks like things did increase a little bit by about $25, but maybe that's just a random glitch. Maybe that's just because she happened to select apartment complexes that were a little more expensive. At the alpha equals 0.05 level of significance, is the student's suspicion substantiated? Assume that apartment prices are normally distributed. Okay, well, let's get to it. Step 1. The null hypothesis is that the mean hasn't changed, right? It's the same as it was back in 2020, right? The mean, the average apartment price is $1,275 per month. The alternative hypothesis is the statement that this student is trying to prove, right? She's trying to prove that the price has increased, right? That mu is now greater than 1275. Well, what evidence does she have in her favor? Well, she collected a sample of apartments and found that the sample mean was 1,300, okay? And that is bigger than 1275, so maybe she's right, okay? The only way to know that for sure is to compute the p-value. We have to compute, well, what's the probability that she would have obtained this if this were true, okay? So let's do that. We're going to use the inference for a mean app from Art of Stat. When we do that, we have to enter in something for the sample mean, which, we said earlier was 1,300. We also have to enter, excuse me, we have to enter in something for the standard deviation, sample standard deviation, which it says that her sample had a standard deviation of $23 per month, so 23 there. And then we also have to enter a sample size, right? I think her sample size was 16 apartment complexes. So n equals 16. We'll punch all of that into Art of Stat, and we'll see what we get for our p-value. So let's head over to Art of Stat and punch those things in. Okay, so I want to do my own. I have some summary statistics. So the sample size was 16. The sample mean was 1,300. The sample standard deviation was 23. And once again, we don't want a confidence interval, we want a significance test. The null hypothesis was that mu equals 1275. And we didn't want to run this two-tailed, we wanted to run it right-tailed. We wanted a greater than sign here in the alternative hypothesis. And it looks like we're getting a p-value of 0.0003. So let's write that down. Okay, now we can use that p-value to make a decision. Okay, we compare the p-value to alpha. Alpha in this case is 0.05. And what we want to know is our p-value less than alpha? And in this case, the answer is yes, right? The p-value is less than alpha, so we reject the null hypothesis. Okay. Finally, we can write out a conclusion, right? The conclusion addresses the original claim, right? It's a statement about what our decision means for the alternative hypothesis. If we are rejecting the null, which we are in this case, then that means we have sufficient evidence to support the alternative. Okay? So there is sufficient evidence to conclude that apartment prices have increased since 2020. Okay. So that's how we run one of these tests. Okay, let's do another example together. This one has some data here. So once again, there should be an Excel file with this lecture on Canvas that you can download, and that way you can just copy and paste the data. You can also punch it in manually into Art of Stat if you want, but it's easier to copy and paste. When you're working on homework, you can copy and paste the values from the homework as well, or at least you should be able to on most of the problems. But let's read this scenario. It says, according to the United States Mint, quarters weigh 5.69 grams. A researcher is interested in determining whether the state quarters have a weight that's greater than 5.69 grams. By state quarters, like the standard quarter is the one that has the eagle on the back, right? But starting around the year 2000 or so, they started to produce these quarters that had different symbols for different states. So you probably know what I'm talking about. But anyway, these things, just as an aside, these things used to cause problems with vending machines and stuff. Because they weren't like the standard eagle quarter, and so they had to like recalibrate their machines. I remember this. I was in like 7th or 8th grade or something at the time. So anyway, so this researcher wants to know if the state quarters have a bigger weight than the eagle quarters. So he randomly selects 18 state quarters, weighs them, and obtains the following data. We're supposed to test his claim at the 0.05 level of significance. Now, to get the p-value, you're going to have to enter that data into Art of Stat, and you'll need, so I haven't shown you how to do that yet. So what I want you to do is just pause the video, see if you can write down the null and alternative hypotheses, and then we'll walk through the remaining steps together. So give the video pause and see if you can do that. Okay, here's my solution. So step 1, right, our null hypothesis is that the average weight of the state quarters is the same as it is for the eagle quarters, right, which is 5.69 grams. So mu equals 5.69. The alternative that we're trying to test is that mu is bigger than that, right? That mu is greater than 5.69 grams. Now for step 2, we want to know what's the sample evidence that we have in favor of the alternative hypothesis, right? And we weren't given that information. We don't know what X bar is yet, but we can get X bar from Art of Stat. So we'll go over to Art of Stat and we'll figure out what X bar is. And then while we're there, we'll get the p-value. So we're going to use inference for a mean. And we're not going to enter any sample statistics because we actually have the raw data. So instead, we're just going to enter the raw data. Okay? And then Art of Stat will do the rest. Okay? So it'll spit out a p-value for us. Let's see what we get. Okay, so in Art of Stat, you're going to want to go to your own, right? We don't want to do an example from the textbook. We have our own data. Don't go to summary statistics like we did before, because that's just going to take you here where you have to put in the sample size, sample mean, sample standard deviation. I suppose you could find those things and then enter them, right? You could find them using Excel or something like that. But it's much easier to just enter the data. So you're going to go down to your own, and this gives you a place where you can enter the raw data. And now from here, you can just copy and paste the values over from the Excel file, just copy and then paste them here into the observations box. Okay, so once you have copied and pasted those values into the box, then we're going to, well, notice first of all, they give you the sample mean, they give you the sample standard deviation, right? So they compute those things. They also even give you a histogram and a box plot, which is kind of nice. You don't have a ton of control over like your class widths and stuff. So I wouldn't necessarily use this graph. I think you can use better tools from Artistat to get graphs, but it's nice that they, include that here. But down here under type of inference, again, we want to run a significance test rather than compute a confidence interval. And we do still have to put in the null value, which was 5.69, right? Our null hypothesis said mu equals 5.69. And we wanted to test to see if our state quarters were heavier, right? So we want a greater than sign. We want to see if mu is greater than 5.69. And there's our p-value, right? 0.1555. So our sample mean is about 5.70, and our p-value is 0.1555. Let's write those down. So our sample mean was about 5.70, which, sure enough, that this is larger than 5.69, but it wouldn't be super unusual to get that value, right? Because just by random chance, you're going to get some quarters that weigh a little bit more or whatever. In fact, the p-value that we just computed is 0.1555. In other words, there is about a 15% chance that we would obtain a sample mean of 5.7 if, in fact, the null hypothesis were true. Well, 15.5 is not very small. Like, that's a pretty large probability. So it doesn't give us any reason to suspect that the null hypothesis might not be true. And so we do not reject it, right? So I'm getting ahead of myself a little bit. But yeah, that's going to be our decision. Do not reject. We compare our p-value to alpha. Alpha was 0.05. And we ask ourselves, okay, is our p-value less than alpha? And the answer this time is no. So we put a slash through it. Our p-value is not less than alpha, so do not reject H null. Okay? Since we're not rejecting the null hypothesis, that means there's really not sufficient evidence to support the alternative. And that's what we would say in conclusion. Okay, there is not sufficient evidence to conclude that the state quarters weigh more than the standard quarters. Okay, and that's it, right? So that's how we run a hypothesis test on a mean. Again, if you're working through homework questions and you want to look at examples of how to do this from beginning to end, then it looks like examples 2 and 3 are going to be the things to follow. So that'll do it for now, and I will check in with you in the next section.